Hey, class, we're starting a new chapter today, and today's chapter is all about what are called Z scores. And I have a couple stories that I can tell you about really the couple times in my career where I've had to use Z scores, and for very different reasons, but interesting reasons. I think you'll find them interesting. So I'll tell you a little bit of story, a couple stories about Z scores as we go through the chapter, as they are really easy to calculate and pretty simple to understand. But I think the stories can help kind of bring them to life and show how these stats are used in the real world. So I'm going to switch to my PowerPoint now and talk over that. So as we walk through the chapter. Let me move my little thing out of the way. There we go. Too far. There we go. All right. So this chapter is all about the normal distribution Z scores, as it says here, and as this cartoon is attempting to illustrate. Another word for Z scores is a standardized score, right? And we're probably used to hearing that phrase because we think about standardized testing, and that's my first story about Z scores. Um, So when you hear like a standardized test, there's a couple ways that you can do that, right? That you can standardize a test. One is through the methodology of the creation of that test and the implementation of that test, and the other is using statistics. And then I guess there's a third where you kind of do a mix of both. So I thought I would talk about an experience I had back, and this was been in 2008. Um, so I was hired as an independent contractor by the Kern High School District, here in Bakersfield, to look at No Child Left Behind scores. I don't know if you remember that educational initiative. Some of you are probably too young, to remember that. You were maybe just a part of it, but the idea was that the idea, like, it sounds good on its face, right? That we should say, here's the educational standard, and we want to make sure that our students meet this standard, right? So then how do you set the standard, and then how do you measure students to make sure that they are meeting that standard? And so I mentioned there's a few ways to do that. The first is to create, one test that every single student takes at the same time in their educational career, and you set the benchmarks ahead of time. Right, here's what we expect for an average score. Here's above average, here's below average, and you put the students into categories depending on how they test. Right, so if that's the case, then you better make sure that every single school has the same type of variability or the same type of diversity within that school, so that they're all on equal playing field from the beginning, and that the test actually is um, gives you a bell curve every time you use it, right? So that's a tough thing to do. It's a not a terrible goal, but it means that you'd have to make some pretty big changes to make sure that every school has the same amount of diversity or randomness going in. Like um, you know, you would expect differences between, let's say, it's like a verbal test or like a test on writing, right? Well, you would expect the schools, whatever school it is, like maybe their honors students to perform better on the test than like their college prep students, if it's a high school, better than the general class, better than classes, remedial classes, um, and you would get some kind of curve like that, with most people being somewhere in the middle, right? Um, it's not a bad idea, but what do you do about students that maybe like English is their second language? They just happen to be juniors in high school. Does every school have the same amount of those types of students? Well, we know the answer is no, right? So there's questions about doing the test that way, and then who creates the test as well. Is it created by educators? Is it created by politicians? Who's creating the test itself? Um, or, right, you could just do that, right? And those things that you should consider no matter how you do your test. And that means that every single student takes the same exact test. Um, and then you have the second way to do it, which is, one of the big debates in education is like, do you measure progress, or do you set a benchmark and strive to aim for it? So if you want to go for progress, and see if students are actually learning over time, right? They're getting better as they go through classes, that kind of thing. It's different ways to test for that. If you're going to use what are called z-scores, then you'd say, okay, well, here's that school's average score. And if you get this nice bell curve, you can say, okay, here's the average score. Now, next year when we do this test, we aim to move that average for this school. And so then you can measure schools on their progress based on their own starting lines or their own baselines. So that the question becomes, do you give each school their own individualized baselines and then test them to see if they can increase their baselines over the years? Or do you say, here's the benchmark, try to meet it, and if you can't, there will be consequences, that kind of thing. So there's different ways to do that. Both have their pros and cons, right? So for us in our country, we decided to go with the first example I gave you, where we create one test and every student takes it. Okay, so the Kern High School District called hired me and a team of people. It wasn't just me, right? Worked on a team of, I think there were about 8 of us, who looked at the data independently, like one at a time, and then we brought all our data together within the group of 8 to see if we got the same test scores on these standardized tests. And we did, because it was pretty simple statistics. It's all descriptive stuff I'm showing you guys how to do. So, we had access to software. We just ran through the software and we're like, okay, here's the mean, median, mode, range, standard deviation, variance, and here's a z-score, right? So that was easy for us to do. We all got the same outcomes. It was like a class assignment, essentially. So that was cool. We're like, all right, we're all on the same page. And then our job was basically done. They hired me back one more time to come back because they said, okay, do you want to be part of essentially what became a lawsuit between the state and the federal government? They were in, what do you call it before it goes to court? It was like an arbitration, basically, with California and the company ETS, which helped design, distribute, and analyze and report the results from this test, all at a big, big, big price, right? So it was pretty weird conflict of interest there. And that's kind of what the state was saying. The state was saying, for this company that creates the test, distributes the test, grades the test, reports the results of the test back to the government, and this all impacts funding for schools, is there a conflict of interest there? Would they serve to make more money if they reported that the school's test scores were low? Because that means that their business gets to continue and doesn't cease to grow, right? So that was kind of the lawsuit. That's what they expected, because what I also found out was my group of 8 people, we all got the same exact outcome for our data, same descriptive stats. And we were not the first team. We were like the 6th or 7th team, something like that, of like 8 to 12 people. And across the board, unanimous, we got the same descriptive stats. Like I said, it wasn't difficult to get those numbers. You just had to crunch them. So we got the numbers, and then the problem was that they were not the same numbers as ETS, that this company that was hired by the government to do all the test prep, testing and analysis. So the lawsuit was basically to say, hey, these guys at this private company here are basically lying about these test scores. And now that was a big deal, because with No Child Left Behind, if you ever do any history, pretty interesting, was that you had to increase your school's performance by like X percentage every year, or you were like defunded, right? You lost funding. And so we looked through those numbers and we said, all right, at this rate, it looks like almost, I wouldn't say almost, a majority of schools will be defunded even more than they already are, um, based on these test scores in about 3 years' time. And so it was really interesting getting to go to the courtroom to hear all these debates. And I was there, and the other people representing public ed, just basically to hold people accountable, make sure they're doing this thing correctly. And we had to go in front of this, judge and say, okay, here's a z-score, here's how you calculate it. And that was interesting, because the whole defense from this ETS company was that z-scores are misleading and that we were trying to trick people and that kind of thing. Also learned, I'm gonna get too like conspiratorial on you, but this was the experience I had there, was that there were many Congress people and even some senators who dropped in because this was a public, you know, public arbitration hearing. I think I'm thinking is the right word, arbitration. I think who were dropping in, and we got to kind of talk with them, and that was interesting. And Republicans and Democrats and Independents, they were all coming in, and we got to talk to them. And what we heard from a lot of them is that they essentially wanted to privatize education in our country. That was kind of their goal. They wanted to kind of do away with public education, um, and use cases or use this No Child Left Behind data to say, we're justified in doing so. Um, pretty pretty interesting stuff there, right? And their whole defense was that Z scores are misleading and they're lies and that kind of thing. So I thought, all right, we need to talk about what Z scores are. If there's a judge who's got a college education and oversees hearings that involve statistics all the time and doesn't know what a Z score is, like that's not good. So I'm going to show you guys today what Z scores are, and I hope you don't find them to be misleading. I seriously doubt that you will. So let's get to it. Okay, so a Z score, another name for them, like I said, is a standardized score. And let's look at some notation first. All right, so our new stat notation here really has two parts. So if we're looking at this on the screen where it says Z equals plus and minus 2, there's really two things to focus on within this plus and minus 2, right? And the first thing you want to focus on is the plus and minus symbol. That simply just means, is this score, like we're talking about one score in this case, is it above or below the mean? So if there's a plus sign there, that means it's above. If there's a negative sign, it means it's below the mean, right? And if it's a plus and minus, then that means it's on both sides. It means it's going out in both directions, above and below the mean by 2, right? So the sign, don't focus on we tend to think of like the negative as being a bad thing. In this case, just think about it as direction. Is it to the right or to the left of the center, right? And then the second part is the number itself, the 2, that's how far. So here's first, this is the plus and minus is the direction, above or below. And then the number itself is the distance. So it's like how far above, how far below, right? And we're measuring that in standard deviations. So how many averages from the center is a certain score? That's a standard deviation, right? Average from the mean, average from the center of your distribution. That's all it means, like how far above and below is a certain score, right? So it looks something like this, right? So if you're looking at a distribution, right there in the center where we see this dash line, right here in the middle, this is our average score. It's also our mode and our median, our mean, right? It's all three. But let's just focus on talking about it as the mean, the average, right here in the middle. And it is 0 standard deviations from itself. That's why it's labeled 0. Like that's the starting point, right? That's the score that has the highest majority. It's the score that creates the 50th percentile, and it's the average score right there in the center because we have this nice normal distribution. Okay, now the numbers down here at the bottom, right, +1, that means 1 standard deviation above the mean. So I'm saying above because there's a plus sign, and 1 for 1 standard deviation, right? Now, if you go the other way to the left from 0, right, over this way, then you move 1 standard deviation below the mean, right? There's a negative score there. And what's significant about that is within this area above and below the mean, you get 68 roughly. It's a little bit more than this, but 68% of the scores fall within 1 standard deviation above or below the mean. So we can say, okay, that majority of scores are right here within, this range, 1 standard deviation above and below the mean. If you get outside of that, well, now we're getting into scores that have a much lower probability of selecting at random or occurring at random, right? Either way, you can see how the curve slopes down. There are fewer scores in kind of, this range between 1 and 2 standard deviations below, or 1 and 2 standard deviations above the mean. Not nearly as many scores there. They still exist, but they're still there. They'd be considered atypical scores because the majority of scores don't fall within that range, right? And if you go beyond 2, right, like above 2 or beyond 2, or below 2, beyond 2, below 2 on the other side, then those scores are extremely rare, extremely atypical, and we're getting into, outlying scores. Certainly don't represent the majority of people. So imagine these are those high schoolers' test scores, right? We expect, okay, 68% of those high schoolers' scores are within this range right here. So if these were letter grades, right, and this is a C right in the middle, you'd say, well, most scores are between a D and a B. There's not as many A's, there's not as many F's. Most scores are like right here in the middle. Right? That's kind of what a z-score does. We just take a distribution that already exists, that has actual scores, like a raw score, like a number. Like you take your exam on the last, your score on the last exam in our class, and you would say, okay, my actual score was, 40 out of 50. It's like, okay, how far away are you from the middle for our class? All right, so really you need to know the average score for the class. You need to know the average distance from the middle, and then you can compare your score to the majority of scores, right? And if it falls within this range, you go, I scored like most people in the class, right? If it was outside the range, you go, oh man, I performed better than the class. If you're out here, you go, oh man, I'm one of like the 2 people that really ace this sucker. And then you could look at the other side too. You could go, okay, well, if, here's the normal range right here in the middle between 1 standard deviation above and below. And if you're below that range, you go, oh, I didn't do as well as everybody else. And if you're way out here, right on the left, beyond -2, you can go like, man, I'm one of the, few people that kind of flunked this exam, right? So you can kind of put yourself, um, give yourself some perspective compared to everybody else's scores within your sample or your population, if you could measure everybody. So that's the basic idea with z scores. But I'm going to give you one little last little thing to kind of to practice here. I'm going to go to my whiteboard to do that. So let's kind of draw out what I was just talking about. Okay, so let's say we have a normal distribution. And by the way, I want you guys to practice drawing a lot. From here on out in the class, really, we're going to be drawing lots of bell curves. You're going to get a lot of practice, right? Okay, so here's 1 standard deviation above, here's 1 standard deviation below, and then we set the mean at 0, because it's 0 standard deviations from itself. Now in this range right here, we have roughly 68% of the scores. So that's what I was trying to say before, right? Like this surrounding the mean, right, which is right in the middle, is 68% of everybody's scores. And if you're on the outsides here, then you're really in the tails of the distribution and you have an atypical score. And so what a z-score allows us to do is to say, okay, is this score fall within 1 standard deviation, or usually where we expect the score to fall, or does it go above or below 1 standard deviation? And we could say something's different about this score. It's higher than all the rest, right? Or it's lower than all the rest, depending on what it is. And what we're going to do today is just look at, okay, how do we take a person's actual score and turn it into distance from the middle, right? So we can say, is this score typical, or is this score, atypical, something we don't expect to see? All right. So that's what we're going to do. And hopefully it doesn't seem like I'm trying to trick you with statistics. We're just really relabeling our graph and to express each score in terms of distance from the mean. So the characteristics of the z distribution, which is a normal distribution, it's has to be close to perfectly normal, right? It's like perfectly symmetrical, unimodal, normal distribution, bell curve. You really only want to say use z-scores when you have this type of distribution. If you have a skewed distribution, you can do it. You can still look at z-scores, but it's going to be more difficult to interpret. So we're just going to stick with the bell curve for our class since we're learning about this stuff for the first time. So if we start with a bell curve, our z distribution is going to be a bell curve. We're not changing the shape of the distribution at all. I'm not trying to mislead people. Okay, second, I said before, is that with any z distribution, the mean is always equal to 0 because we're measuring everything in distance and standard deviation units. So that means like, how far away, if you took a ruler, along your x-axis of your bell curve, and, in a ruler, maybe we're measuring things in inches. Now just replace the inches with standard deviations. It's like, okay, well, how many standard deviations away from the middle is my score? Well, you put that 0 on your ruler, right on the middle, and then you measure out from the middle. Instead of inches, it would be standard deviations. So how many standard deviations from 0, right? So we need a starting point, and that's our mean. And then the third is that, standard deviation of any z distribution always equals 1, right? And just think about this as we count out in what we call typical in 1, right? Plus and minus 1 around the mean. And anything beyond 1, is going to have a lower lower proportion of area under the curve, or have a lower probability of occurring at random, right? And that means it's something about it is atypical. Okay, so I'm going to copy this down on my whiteboard here because I'm going to use this graph here as a reference, and this kind of gets me into my second z-score story, right? Okay, so I'm going to copy this distribution down. Just bear with me. I know you can't see it, but we will go to this, my drawing, in just a sec. Copying the names down to Slug, Binky, and Biff. Okay, so what we're looking at here in this distribution, it says our attractiveness scores. All right, so it looks like if we just look at the x-axis, right, go into 0, and this means there were no scores between 0 and roughly 25. So it looks like it's probably a 100-point scale would be my guess if we have numbers this big. So it's like saying on a 100-point scale, how attractive are these three individuals here, Slug, Binky, and Biff, right? How attractive are they? And we could see the average attractiveness score is about a 60, right, on a 100-point scale. So we could probably, really, bring that down to like a 10-point scale. It's like a 6 out of 10, right? So we're going to be like objectifying some imaginary people here, right? So let's look at Slug, Binky, and Biff. Just right away, just looking at it without doing any calculations, we can see that Biff over on the right has a score of 90, which is very different from the average score of 60, much higher, right? So that's probably going to be an atypical score. We'll do the official calculations to find out. We got Slug on the other side. Slug's got a score of 35. And that's much lower than the average score. So Slug 2 is probably, an atypical score. Not many people with scores as low as Slug's, just like there are not many people with scores as high as Biff's. But Binky is close to the average, right? So imagine that you're Binky. Imagine that, this is your attractiveness score, right? So now you're invested on this score. And this would be, okay, imagine how you would do this type of study, and you would have, people look at images of other people and just rate them. Like in this case, you might say on a scale of 0 to 100, how attractive is this person? Now, let's say, one of the pictures they're looking at is yours, right? So you're like, oh man, I don't know what I am, right? You got your own guess in your head, and you're like, I'm probably like an 8, So that would be like an 80 on this scale. People, especially men, tend to overshoot their attractiveness in the eyes of others. That's a different class. There's probably evolutionary reasons for that, but that's a different class. You could take that class with me some other time. But let's say you got Binky and you want to know, am I average? Am I typical? Am I within one standard deviation, or am I outside of that standard deviation? And if I'm outside that standard deviation, I hope it's on the positive side. I hope my score is going outside of these parameters to the right? So I can say I'm better looking than most, right? Or am I somewhere in the center? Now, think about it this way. That's a tough thing to claim because there's a lot of scores within one standard deviation. That's 68% of the scores. So if you imagine 68% of the population is about the same level of attractiveness, and to say that you're higher than that, got your work cut out for you, right? You want to be atypical in that way, though. All right. So the other, the good thing about, well, no, I'll tell you that in a sec. I'll show you how to calculate these scores, and I'll tell you my second Z-score story. All right, so calculating the scores is simple stuff, right? We're going to take that 35 from Slug, the 65 from Binky, and the 90 from Biff, and we're going to turn those raw scores, 35, 65, and 90 are the raw scores. We're going to turn those raw scores into Z-scores. So we're not going to move any of the scores around. We're not going to change the shape of the distribution. We're just going to express how far from the center are each of those three scores. Are they to the right or the left? And how many standard deviations to the right and the left? Okay, now here's the formula to do it. I'm going to copy this down on my whiteboard too. So when I do switch over to my whiteboard camera, you will see all this stuff here in one place. So here's our formula. Pretty simple formula. There's only 3 components to it. All right, so I'm going to switch to my whiteboard camera now. Well, that took a second, but there we go. Okay, so here's my whiteboard. Just copied the distribution, shorthand that we were just looking at. And what we want to do now for Slug, Binky, and Biff is run each of their scores through this formula. So to help out with that a bit, let's do this. Let's say when we're looking at 35, 65, and 90, these are the X scores for these 3 people, right? X is another way of saying raw score, just X, right? And we want to turn those into Z scores. So we'll just kind of create a second number line below here, a second axis. We'll call this the Z axis. And we're just going to relabel each score in terms of how far it is from the center. So we know right here in the middle, this is a 60. So on our Z axis, this should be set to 0. There we go. There's our starting point. And now all we have to do is run these scores through this formula in order to solve, to find the Z-score for all 3 of these people. You'll notice we're missing something, right? We got the X values. Those are these numbers. These are the X's we want to change and transform. We got the average, right? That's up here. That's 60. But we don't have the standard deviation. So I'm just going to give it to you in this case. Let's say that the standard deviation is 15. So it's like an IQ test, right? So standard deviation is 15. Now we can just plug these 3 numbers in to our formula and solve for each person, right? Standard deviation, we got the mean, and then we got our 3 X's here. So let's look at Biff first. All right, so for Biff, he has a score. I'm assuming, I don't know if it's a he, right? Slug, Binky, Biff, they sound like he's to me, but whatever. They, all right? So they have a score of 90, and we'll subtract 60, right? 60 is the average score. So this is the population average. So that's where the 60 came from, right? I just gave it to you. So we have 90 subtract 60, and we're going to divide that by our standard deviation, right? Standard deviation is right here. It's 15. So this becomes pretty easy, right? If we break this down, that looks like 30 over 15, right? And what is 30 divided by 15? We get 2, but you should express it like this because it's a Z-score. It's plus 2.00, right? So Biff is 2 standard deviations above the mean, right? Like there are not very many people that would be 2 standard deviations above the mean. Tiny, tiny percentage of the population. If you're saying on a 100-point scale, how attractive is somebody, these are the people that are getting like 90s, right? 90 or better. Not very many people. So like you would notice Biff. Biff's walking down the hallway, Biff's turning heads. You're looking for sure, right? You're like, whoa, right? Okay, now let's do the same thing for Slug. So I'm going to erase Biff's info and do the same thing for Slug. You'll see that we're going to use a lot of the same information. We're just going to change the X value. So Slug's X value is 35, and we want to know how far 35 is from 60. So already we know it's going to be a negative answer, and we're going to divide that by 15. So that gives us a negative 25 over 15. So for Slug, if you work that math out, you get a negative 1.67. 1.67 negative for Slug. Now the negative just means to the left, right? Less than the average. So poor Slug, right? So Slug is 1.67 standard deviations below the mean. So outside of that range of 1, it's like below -1. So already Slug is like atypical in their score, not looking kind of average attractiveness. They're below average attractiveness, which is a bummer. And they're pretty far, right? They're almost as far as Biff is in the opposite direction. So there's not very many people who are as genetically unlucky as Slug to be this far to the left uh, on this distribution. Poor Slug, right? So Slug would turn heads too, probably in the hallway, right? You go like, what? What happened? What happened to Slug, right? Okay, poor Slug. All right, now let's look at Binky, kind of right there toward the center. So for Binky, and this is the one that I said, imagine this is your score. I say your score is 65, and you want to know, do you fall within the typical range? Because man, you feel atypical, you feel better looking than average, but let's find out for sure, right? What did everybody else say? So Binky's score is a 65, right? And you might say 65, the average is 60. I got a 65. I'm above average. We go, hold up. Maybe, right? Let's see if you fall within that range of typical attractiveness or not, or what we would expect to find from a random person. So we go the difference from my score in the middle, right? So I already know, okay, that's 5. That's easy. And we're going to divide that by 15. So we know it's positive, right? And we're going to hold on to that no matter what happens, right? It's to the right. So 65 subtract 60 divided by 15. Well, that gives us 5 divided by 15, which is 0.33. So we would say for Binky, that score of 0.33, 0.33 standard deviations above the mean. All right, but still within the range of 1. So Binky is from statistical accounts, average in physical attractiveness. So, of course, being human, you would still try to decide which could you use to your advantage. Do you want to use your X value or do you want to use your Z score? Your Z score says you're within the average range of attractiveness, or at least you're within the typical range as everybody else in terms of attractiveness. But your X value is more difficult for people to understand because it says you're 5 points above. So you just go, I'm above the average. I'm better than looking. Or I'm better looking than the average person. But the Z score says, nah, you're kind of in the same boat with most of us, right? But there you go, right? That's the Z score for you. You can see that I didn't change anything. I didn't move any scores around. I didn't do anything to try to trick people with statistics. If anything, we made things a little more clear using statistics by what we mean by typical and atypical scores. Not too bad, huh? Not too complicated for, to find an X value. All right, let me go back to my PowerPoint for a sec. That means you got to look at my face for a moment. Hi there. Okay. So the formula, if you have an X value, and you want to transform it into a z-score is just like this. Simple stuff, right? Oh, you know what? Let me show you one more thing. Before I do this, let me stop sharing. All right, so you might see that this is, if you have population data, this is what the formula looks like. You might also see it written out like this. Right? So, whoops, that's kind of a sloppy S. Let me try that again. There we go. So you might see it like this if it's expressed, if you have the distance between an X value and an X bar, which is also an average, and then S is a sample standard deviation. If you're just talking about a sample and you're not saying this sample represents a population at large, you're just talking about your one sample, it gets tricky with the terminology, but you're essentially treating it as a population if you're not going to make any inferences about a broader population from it. But nonetheless, people will use, this type of notation. So X average divided by standard deviation, which is the same as this X average standard deviation, right? Just a different way to express kind of the same thing. But this, I would say, is for a sample with no inference. So if you're just going to talk about your sample and you're not going to say, here's what I got for my sample, and therefore it means this for the population at large, you just want to talk about your sample alone, you might see different notation in that regard. But it's essentially the same thing, right? I just don't want you to be confused by that in case you run into that issue. Okay, now let's look at our next formula, because if we can find a z-score from an X value, we can reverse that process, right, with this formula here. So this formula is if you have a z-score, but you want to know its original X value, right? Okay, so erase some of my work down here. All right, let's put a fourth name in this study. Let's say that with this formula for finding an original raw score, I'm writing it down on my whiteboard so when I switch over, it won't be alarming. Let's say, all right, you're a part of the study, and what I mean by that is that you're someone who there's a picture taken of you, and other people are rating you for your attractiveness, and you want to know how you did, right? I mean, I would want to know. I'd want to know, like, how do people score me? I'm pretty sure on a 100-point scale, I'm at least a 90. At least I gotta be. But for the rest of you guys, I mean, you want to figure it out for yourself, I'm sure. Let's say you have, I'm the experimenter and you were a part of the study, and you come to me and you go, how did I do? Right? Maybe like 100 people rated my picture. How did I do? I want to know how attractive they think I am. And I tell you your z-score, and I go, well, let's say you have my name. I go, well, Jordan, your z-score was, I don't know, let's say it was plus 0.65, right? Imagine that scenario. You go, hey, how did I score in the study? What was my attractiveness score? And I go, you were 0.65 standard deviations above the mean. And you just look at me like, okay, easy for you to say. Can you put that back into, the 100-point scale units so it makes sense to me? Right? That's what you'd want to know. So let's say you have this information about yourself, and that doesn't really make any sense to you because you don't know what a z-score is. Then we have to know some other information too. We have to know the average, right? And we have to know the standard deviation for, this data set or this sample. So we can just plug it in and solve. So we want to find X, right? So we do X equals, and then we put in our z-score here, plus 0.65 multiplied by the standard deviation, which is 15, right? So I'm just putting this in there. And then we add the average. The average was a 60. So we're literally walking through the formula backward when we look at it this way. Remember before we subtracted and divided, well, what are we doing now? Multiplying and adding, right? So we're moving backward through this formula. So we're just going to go a step at a time. In fact, let me get my phone calculator and we'll do it in real time here. Okay, so let's start here. Let's do this multiplication, these parentheses first. So we've got 0.65 multiplied by 15 equals a 9.75, right? So we get 9.75 plus 60. So we'll do plus the average score of 60 equals a 69.75. All right. So on a 100-point scale, you get a score of 69.75. And your z-score is 0.65. So you are basically average, right? You're within that average range, or at least within the typical score range. So you kind of look like everybody else in the population, right? There you go. And I don't know if that makes you feel good. Or which score would you rather hear? Say like, well, your 0.65 standard deviation's above the mean. That might sound better, even though you don't know what it means exactly. That might sound better than saying like, I'm roughly a 70 out of 100 or a 7 out of 10. I don't know, right? Or maybe you start to argue, yeah, I'm in the typical range, but man, I'm pushing it. I'm getting toward the border of that typical range. um, okay, so you can go back and forth with z-scores and x values. If you have an x value, you can turn it into a z-score. If you've got a z-score, you can turn it into x. You for sure will be asked to do this on the quiz and the next exam, a couple weeks from now. So, make sure that you're comfortable with these two formulas. Oh, and the other thing, if you're wondering, where these numbers came from, well, you can't solve this problem without these descriptive numbers, without the average and the standard deviation. So in a lot of cases, in most cases, I'll give them to you. But if I don't give them to you, you guys learned in the previous chapters how to calculate an average and how to calculate a standard deviation. So it wouldn't be a stretch for you to be able to have to do that yourself if you started with the raw data. You would just have to back up into the previous chapters and remind yourself, how do I calculate an average? How do I calculate a standard deviation? And once you got them, you can plug them into these formulas, and then z-scores are no sweat. Okay. So let's see where we were on our PowerPoint. So we went from x values to z-scores, then we went backward from z-scores to x values. And we, relabeled our, whoops, the numbers are a little off because I use different numbers than the example in your book here, but you get the idea, right? They used a standard deviation of 10. I used one of 15. And so our numbers came out a little bit different. Here's another example where you might use z-scores for yourself. In this case, let's say that you're trying to figure out, are you a better English student or a statistics student? You probably have a sense of that already, but if you're like, I want to figure that out mathematically somehow, what am I better at? And how do I do that? How do I even compare where, in my stats class, I have to turn stuff in almost every day, and there are a lot of points available. And let's say the whole class in its entirety has like 1,000 points, right? And maybe you're approaching like the midterms and there's like 500 points were available. Or in your English class, maybe you've only done a couple of assignments and they were worth like 50 points each. So you got like 100 points. Well, how do you compare one class to another when, the point system and the grading systems are so different? Well, what you could do is, calculate your z-score in your stats class, then calculate your z-score in your English class and see which one is further from the center, right? So if we look at this graph here, let's look at, we got two people. It looks like we have Millie and Althea. So if we look at Althea first, right, and say her z-score for her English class is 0.5, so she's half a standard deviation above the mean. And then her statistics class, she is 1.6 standard deviations above the mean. So we're looking at, in that case, remember typical and atypical scores. If you're within one standard deviation, that's a typical score. It's where most scores are. So she's doing, average. She's doing like most people in her English class. She's above the average, but she's not outside the range where, it's atypical. So she's probably looking at like a C. She's probably in like the C range, maybe C plus, maybe, right? And in her statistics class, she's 1.6 standard deviations above the mean. So you're like, okay, well, if we say the parameters for typical end at 1, then she's beyond 1. She's at 1.6. So she's doing better than, the majority of people in her class. So she's probably getting up toward the like B plus A range here within her statistics class. And she's further away from the center in stats than she is in English. So she's a better stat student at this point in time. And then for Millie, you could say the opposite, right? Millie is one standard deviation below the mean in English. So she's just barely there with, the typical scores for the class. So she's honestly not doing great in English, but she's doing even worse in statistics, being 2 standard deviations below the mean, right? That's just like Biff in our last example, right? That's an extreme score. So she's probably flunking statistics and not doing so hot in English either. But comparatively, she's a better English student than a stat student. So I show you this example here of comparisons of two z-distributions to kind of give you an idea of how they can be used, right? So you can say, here's where I stood at this point in the semester, comparing these two classes with very different point systems. Here's where I stood later in the semester, see if they change. You could look at it that way. Another good way to think about, z-scores and their usefulness is that you can then compare um, like point allocation systems, and you can still combine them. Like, so here's an example of that in my own research life. So years ago, the American Psychological Association used to put on these contests where you would apply for grant money. This was a long time ago, and if they accepted your proposal for research, then you get some money for it, and it pretty much meant there'd be like a little spotlight on you as you do that research. And the research was usually replicating something that had been done in the past within psychology. And so when I was in college, we got approval and funding to do one of these. And what we replicated was a study done in the 70s about casual sex, right? So the casual sex study in the 70s just looked like this, where they were comparing male and female actors or confederates, we would call them in research, as they approached, strangers on a school, like on a university campus, and they just proposition them for casual sex, right? They walk up to strangers and say like, "Hey, would you like to have sex with me?" I don't remember the exact wording, right? And then people would say yes or no to them, and they would keep track in their pockets, like who said yes, who said no, right? And so the APA said you get to add one independent variable to that classic study, and then um, if we like it, if we choose yours, then we'll help you carry it out. We'll give you funding and that kind of thing. And that was exciting, right? So we applied and we added a dimension of attractiveness. So we said, okay, we think it matters whether you're male or female and you're asking people if they want to have casual sex with you. We also think it matters how attractive the person doing the asking is. And that may be different for men and for women, or it may not, right? But let's find out, right? And so that's what we did. So we had to get like 3 different groups of men and 3 different groups of women to be our actors, to go out and proposition people to see if they would have sex with them. We had to find like the average looking people. That was really easy, right? That was like, typical attractiveness. So it looks like roughly 68% of us fall in that category. Super easy to find those participants. And they're usually not like too offended if they find out they fall into that category, because there's like comfort in numbers, right? Like, oh, I'm like most people. Okay. right? Hopefully I can rely on some other attributes to attract somebody to me other than just my physical attractiveness. Okay, and then you have people on the high end, right, who are like, what would you call them? Like genetically blessed, right, to be very attractive to others. And those people were more difficult to find just because there were fewer of them than what is the general population. But those types of people who know they're attractive, probably because they've been propositioned by so many people in the past in their personal lives, they probably get a sense that, okay, I'm good looking, right? And if you're doing a study where you're calling for actors based on attractiveness, they're probably more likely to sign up than people who fall on the opposite end of the scale. So the people like the slugs in my last example, for men and women, those were the hardest to find. And one, because there aren't as many people that fall into that category, and two, you know, for like emotional reasons, I'm sure they're not going to go sign up for a study about attractiveness if they already kind of probably have an idea that they're not attractive to most people, or compared to most people, their attractiveness is atypical, and in this case in the negative direction. um, Man, so if the positive side outliers are genetically blessed, what will we say? No, how about this? We say they're like aesthetically gifted or aesthetically lucky. Then the people on the other side, right, the negative side, maybe they're like aesthetically challenged. Oh, it sounds mean. Or like aesthetically unlucky, right? But we found them all, and enough people in all three of these categories, and being six groups, three groups of men, three groups of women, set them loose on the college campus, and they gave a compliment, and they asked people to have sex with them, and they had two little clickers, like one in each pocket. You might see if you like go to a concert or somebody's like counting the attendance, and they just go click. That means one, click another one. They're just adding in their pocket. So I think it was like right was someone said yes, left was someone said no, right? And so we replicated the study. Now, the problem was we wanted to combine our data for attractive people and casual sex, and attractive people sex, men and women, and casual sex. And we wanted to combine it with schools that were not in Bakersfield, because the one criticism was like, okay, you guys are, uh, they said, oh, you're in California, so people will be more casual. It's like, I don't know if that's true for starters. And then it turned into, oh, and you're from Bakersfield, and Bakersfield's different than California. So we want to combine your data with other schools in California. So we're like, okay. So we got to kind of work with, what was it, UCLA, and what was it, Sacramento, that we combined our data. But we weren't told that until after the fact. So we'd already collected our data, right? We already had our scales for rating who's attractive. We did a pilot study. We go, this is tell you how long ago it was, look at these Polaroids of people and rate them for their attractiveness. Well, they did the same thing at UCLA, same thing at Sacramento. But we used a 0 to 10 scale because we thought like that's how people talked about attractiveness of others. When you're objectifying people in public and you go like, what's that person over there? And you're like, damn, they're a solid 10, man. And then, that means they're super hot, right? So we thought like, that's what people are used to talking. We'll use a 10-point scale. And the scale is kind of arbitrary unless you got to combine it with other people. So at UCLA, they used a scale that was like 1 to 6, I think, something like that. And then Sacramento used like a 0 to 7 scale for their pilot studies for rating their models or their actors for attractiveness. So we're like, well, how do we combine all of our data so that we can get our 6 groups? You got to convert it in some way. So we used Z-scores for all of our scores for attractiveness, right? And then we could combine our data in that way. So you never know. Right? That's one other reason how Z-scores could be effective, right? For combining data. Okay. Now, another thing about Z-scores that's important, and you know what? Hold on a sec. I think I'm gonna stop here, and I'm gonna make a second Z-score video because this is getting pretty lengthy. So I'm gonna come back in just a sec with a second Z-score video for you, and we'll talk a little bit more about them. We'll break this chapter into 2 parts. I think it's better that way. So um, go click on the second Z-score video after you've watched this one.